online and get the square grabber link. And you needed to play it 15 times. So for activity 1, collect your data, and then what we're doing is we're putting it into the graphing calculator. So did you guys use your school computer to do this, or a phone?
I use my computer.
Yeah, I don't think a phone will work because phones don't run on flash. At least iPhones don't. So that's the game. Can I use one of your sets of data? So, what kind of horizontal axis are you guys going to set your window on? Yeah, 0 to what?
Would be the third.
Will 20 work horizontally?
I need more.
You need more than 20? What do you need? What does yours need to be horizontally? So we gotta go bigger. We're gonna be able to project out. Say it was yours horizontally to 25.
No.
25, what's the biggest one?
36.
Holy canola. We'll just do it to 40. Does that take yours in, Avery?
Yeah.
Go to window. And then your X minimum. I gotta be able to talk through this thing too. Shoot. In case Logan's watching, or Nick. So, put everything into lists. N is list 1, and S from the activity is going to be list 2. And then what we're doing is we're setting our X from 0 to 40. What about the Y? What does that have to go to? So that's L2. What's the biggest number you guys have?
720.
720. Do you have something bigger? 750.
1050.
1051. Oh, wow. So what if we went to 1100?
And start at 0.
Yeah, I guess start at 0. Go to 1100. Maybe make your scale like 100 or so. Because here, this is the one thing, we have to know what our scales are. Because we're going to try to pick imaginary points out of this. So this is going to be tough. I'm going on, my X is 0 to 40 with a scale of 5. And the Y is 0 to 1100 with a scale of 100. And then you got to go to second Y equals the stat plot, and you got to turn your plot on for 1 and 2. and then you gotta look at it. This might not be easy. I don't know what to see. It's faster than working on paper, though. So does your stuff look like it forms a line?
Mm-hmm.
Your data look like a line? What do you think?
Not really. Some of them, but not all of them.
Some of them. Let's see them. Okay, so you got a couple outliers, maybe? This is what Lois looks like.
That's pretty good. One.
Second step off. It's on L1 and L2. You have two on. You have number 2 on. Turn that off. There. So is your data looking in here? You got some that are really low. That must have been when you got lazy, huh? Yeah, this is what mine looks like, just like it is. Okay, so other than those, I mean, you have outliers, yes. But the linear, the line is, it looks like it's a straight line, doesn't look like it curves.
Yeah.
Okay, so then what else are we supposed to do here? Let's go right to the book. So we're supposed to estimate coordinates of 2 points. So if we did this on paper, what we would be doing is we would be, we would draw a line on paper, and then we would take 2 points on that line. So it might look like this. So we got N, we've got S, and you got points that look like that. So you say, okay, that's a line. And then you take a ruler and you draw a line of best fit. And now what you would do, if you're on paper, is you would take 2 points that were on the line that you drew. Not points that were data points from your collected data. It'd be from your imaginary line. And what you're supposed to do with those 2 points, if this is x, y, well, not n, it's going to be n and s. If this is going to be some n value and some s value, and this is another one, so that's the first one, that's the second one. What you're supposed to do is you're supposed to find the rise over the run, find the slope, and then determine an equation. And you could write it in point slope form once you determine your slope. So what I would say we should do is, if you go to the trace, you don't have to be tracing any, oh no, you do. You would trace points, my bad. Here's what you can do. If you just, if when you're looking at your graph, you hit the arrows, you can create a cursor that you can move around. And what I would say is, move the thing around to a couple of locations that you could think of as imaginary points if you were to draw a line across your screen. Could you do that? Are you capable of doing that? You get your cursor to come up? Well, you don't need to trace. When you add it on trace. Okay, so second, quit, then hit your graph again, and then go back to there. So like, maybe here, if you drew a line, maybe somewhere around here, one. And then you can look down on the bottom of your screen and you can get the ordered pairs. So try to get yourself 2 imaginary ordered pairs from your screen. Just round it to the nearest whole number. These things give you lots of place values. So So I'm just using my arrows. And then you can see down on the bottom, there's X and Y value. Rounded to the nearest whole number is what you want. And pick two of them. So you're mimicking something like this if you were to do it on paper. So can you find the slope from that? Why don't you do a quick calculation of what you think your slope should be? And then I wrote mine in point slope form. This is what I got for a slope. What did you get, Willow? Okay, so yours is a little different, but that's fine. What did you get for a slope, Taylor?
45.6.
45. How about Avery?
29.
29. Okay, so we're all over the board. That's fine. Probably everyone's going to have a different slope because of how they played the game. You think? I think. We'll see. Okay, so then what I did, point slope form of an equation, I just said y minus one of these points equals my slope times the quantity of, wait, this has got to be x minus the x value from one of those points. Then, what we can do with this is we can move it so that it's, move this 181 over here and combine like terms so that we have an equation in slope-intercept form. Because when we do a regression on the calculator, it gives us something in slope-intercept form. So I'm just going to add 181 to both sides. I'm going to distribute this. And then do some calculations and figure out what mine's going to be in slope-intercept form. You should do the same with yours. What does yours look like? Anything like that? It's probably not really that far away from that. Although it's a minus, huh?
No. That's just, that's.
Or is it the 5, you can add 5 to them.
Yeah, I did. Because it
It's a negative 3. Okay, then it's positive 1, 4, 3. Yeah, that makes sense. What do you do? Yeah, you see how I have y minus 181? I added that to both sides. Because when you start in point slope form, what's your slope? Okay, good stuff on the other page. What's your equation? So, well, there's okay. So if this is that's your slope, then you would write y minus, for example, 463 equals that slope times x minus 4. Are you sure? Yeah, so what I did with this, I called that point my x sub 1, y sub 1, and I plugged that in to the general form of the slope, point slope form. And then here, I'm adding 181 to both sides. And so then I distribute 26.8 times the xn times the negative 4. So then I'm subtracting 26.8. Oh, shoot, that's wrong. I screwed up. Because you have to subtract. No, that's right. That is, I'm okay. Subtract the 4 times your slope. Okay. And then you combine the like terms here after you multiply, and then you get your y-intercept. So then do a regression. Do you remember how to do regressions on this? Yes? No? Okay, so to do a linear regression, you start with stat. I'm sorry, let's make sure Taylor's ready to go. Are you good? Yeah, stat, and then you go over to calc, and then you go down to linear regression. Stat. And once you're on calc, you gotta, I think if you do the number 4, linear regression ax plus b, then it will say which list you're pulling your data from. And you just keep hitting enter, and then you'll get a slope and you'll get a y-intercept. Is that what you got from yours? Okay, so then we have the numbers in there, right? That's what I got. What did you get, Avery?
What do? I just calculate?
Yeah, you hit calculate, and then up comes your A and your B numbers.
29 x plus or minus. I don't.
What is B?
Negative.
Okay, so then you have a negative.
08.
Confused by what you're reading or what? This is what I have. Yeah, so you have about 29.70. And your R2 and R you don't have to worry about. That just says how linear your data is. The closer those numbers are to 1, the more linear your data is. And I mean, we're going to learn about these in FSG, but those numbers show a very, very strong correlation. What did you get? She had a slope of 32 and a y-intercept of negative 58. So y equals 32, which isn't far at all. Minus, yeah, it's almost exactly what you did. So what did you get when you picked your points and you came up with an equation? That's your equation? So that's really close. Those are close. That's really close. Wonderful. All right, so then we have that. Then, I'm just wondering how much we need to do. You know, the second activity, let's look at the second activity on page 177 and talk a little bit about our data too. They bring up some terms. One is linear regression, and what you just did is called a linear regression. Linear regression is many, many calculations being done by your calculator, actually. And what the calculator is doing is this. I'm gonna scribble out a little bit bigger graph here. So let's say we had data points as such. And then we were going to draw a line through. Okay, so if we were to take a point here, if I draw in red, are you going to be able to see it okay? If I do this, can you see that? Yes. Okay, so if we were to look at this point here, see how far it is vertically off of our line. And then from that, we would make a square. And then we come to this point, we do the same thing. And this point's going to be a really little square because it's so close to the line. This one's not so bad. So if we made all these into squares, let's say that that's right on the line. This height here is a vertical distance of, in this case, it's our score. So if we were to look across over here, this difference between the actual score and what the line would predict, that difference is a set amount. This is a smaller amount, so if you come over here, it's a smaller difference between the actual and the predicted score. And if we were to do a calculation where we took the actual and we subtracted the predicted, that's a deviation. That's how far away our actual data is from the predicted data. And what's happening in the calculator in order to figure out that that line belongs there and not over here is that it's finding all of these potential differences between the data and the line, and then it squares that value, and then it adds all the values together. So this is the difference squared, and so on, and it adds it up. It's called a sum of squares. And the idea is to make that number as small as possible. Because, you know, if you had a line that was, for example, out here, then the difference would be huge for some of these points, wouldn't it? Or if you had a line that was on an angle, the difference would also be huge. So sum of squares or least squares line is basically what's being done when a regression happens. And then the question is, how close is that? How close is that to a straight line? Because, you know, you could have, for example, with data that's like this, And that's not really, I mean, it's kind of close to a straight line, but the numbers are really far away from the line. Or you could, maybe if there were a bunch of points down here, it would be hard to get that line to be really close to a lot of the points. So on your calculator, when you get an R value or an R squared, is that showing up on your calculators when you did the regression? I know it was on yours. And, okay. When you get that number being close to 1 says that there's a very strong correlation between the data and the equation. Any numbers that are above like 0.9 means that it's probably a good equation for the data. If you get an R value that's like 0.7 or 0.8, then it's probably not very strong correlation. And then you wouldn't be able to use a regression to model what the data is. It has to be some other kind of equation. So linear regression is finding out what the best line is. This is the regression line, or the line of best fit, or the least squares line. You can call it any of those things. They all mean the same thing. This difference, that's deviation. I'm going to use that word. How far the data is from the actual predicted value. And with that, that's all you need to do this work.